Okay, so we are talking about linear transformation. So basically, just to recap, we have two vector space u and v over the same field F. So we have two vector spaces u and v over the same field F. So a mapping from u to v is called linear transformation if this property is satisfied. T of A alpha plus B beta can be written as A T alpha plus B T beta, and if this is true for all A B coming from the scalar and for all alpha beta are the vector from U, and this will be a vector in V and this will be a vector in V, and that is why we need to have the same field. So, we can operate this. So, this will be again a vector in V. So, if this is true, then we know this is the definition of the linear transformation. Now, we will talk about some operation on the linear composition of two linear transformation. Okay. So, suppose we have three vector space u v w over the same field. So, you have a vector space u v and suppose you have another vector space w, and both are over the same field F. Okay. So, we have basically three vector space and we have a two linear transformation. One is from say u to v and another one is say S from v to w. So, we have another mapping which is S from v to w. Okay. So, then let these two be, let T and S be two linear mapping, linear transformation or mapping. Okay. So, now first of all this is a linear mapping. So, it is a mapping, T and U both are a mapping. So, T is a mapping from U to V and S is a mapping from V to W. Now, if you consider the composition of this is also a mapping. So, composition means we take a element alpha from here. So, we apply T. So, this will give us T alpha, and then on this is the element in V. So, if we apply S on this, so this is S of T alpha. So, now if you consider this mapping, say composition mapping, which is denoted by S compose T, this is a mapping. So, this mapping. So, it is basically a mapping from U to W. So, we take a alpha from U. So, S compose T alpha is basically, we first apply T alpha, then it will be an element in V. Once it is an element in V, we can apply the S on it. So, this is basically our composition, how we define the composition. So, this is the compose mapping. Now, we want to check whether this is also a linear mapping or not, linear transformation. So, that we have to check. So, for that what we need to check? We need to check the we need to take 2 a b from the scalar and we need to verify that. So, this A alpha 1 plus B beta 1 or A alpha plus B beta, A alpha plus B beta, if we can write this S compose T on this, if it can be written as S compose T A S compose T alpha plus B S compose T beta. If we can show this, then by definition this S compose T is a linear function, linear mapping, sorry, linear transformation. Yeah, all are same basically. So, this in short we denote by S T basically. So, this is basically S T, in short we denote. So, we want to show this. So, let us try that. So, S T of this is basically, so S T of this is basically by definition we first apply T on this A alpha plus B beta, then we apply S on this. So, this is basically the composition of two mapping. Okay. So, now how to write this? So, this can be written as so then T is a linear mapping. So, T can be written as A. So, T can be written as A T alpha plus B T beta, since T is linear, since T is linear transformation. So, by the property of linear transformation we can write that. Okay, so, basically we have this. Now, S is also linear. So, if S is linear we can write this as so this is some gamma 1 gamma 2. So, basically A of S of T alpha plus B of S of T beta. This is because S is linear. This is because S is linear. So, that means the ST of A alpha plus B beta is nothing but S of A into T of alpha plus B S of T beta. So, this is nothing but A S T alpha plus B S T beta, and this is true for all alpha beta and all A B. So, this implies S T, which is basically S compose T, is a linear mapping, is linear. So, this is the proof of linearity of this composition. Okay. So, the composition if S and T are both linear, then the composition mapping is also composition function is also a linear function. Okay, now we will define the inverse of a transformation. So, we just define the inverse linear transformation. Inverse of a linear mapping. Okay. Now, we know the suppose we have a mapping from U to V. So, suppose we have a two vector space U V over the same field F. So, this is our T. Okay. Now, we suppose this is a linear mapping. Suppose this is a linear transformation or linear mapping. Okay, now this is a mapping. Now we know the mapping has a inverse if this transformation is 1 to 1 and 1 to 2. So, suppose this T is bijective, basically bijective mapping. That means it is 1 to 1 and on to. Okay. If it is 1 to 1 and on to, then we can have a inverse. So, how we define the inverse? So, inverse is also a mapping. So, this T inverse, which is a mapping from V to U. So, how to define that? So, suppose this is beta. So, this is alpha. So, alpha is going to beta. So, T inverse of beta will be alpha if and only if T alpha equal to beta. And since it is 1 to 1, T is 1 to 1. So, there is only one alpha which is going to beta. So, that means this T inverse is well defined. Okay. This means T inverse is a mapping. T inverse is a mapping because this T is bijective, T is 1 to 1 and as well as it is on to. So, the range of T is covering the whole V. So, that means, if you take any element beta over here, it has a pre-image over here. So, this is a well defined mapping. Now, we have to check whether this mapping is also a linear transformation or not. Yes, this is a linear transform, but that needs a proof. So, we have to check this inverse is also linear transformation is not or not. So, let us try that. So, for that, so let us take T inverse of A beta 1 plus B beta 2. Okay. So, we have say we take 2 point beta 1 and beta 2 in V and we want to write this as for linear transformation we need to. So, this is A T inverse of beta 1 plus B T inverse of beta 2. Okay, so, that means, this is basically how we can write that. So, this beta 1 beta 2 belongs to V, that means, there exists alpha 1 alpha 2 belongs to U such that T alpha 1 equal to beta 1 and T alpha 2 equal to beta 2. Okay. Such that T alpha 1 equal to beta 1, T alpha 2 is equal to beta 2. So, now what we do? We just take this. Now, what is the A alpha 1 plus B alpha 2? So, if we apply T on it, now T is a linear transformation. So, this will be written as A T alpha 1 plus B T alpha 2. Now, A T alpha 1 is basically beta 1 plus B beta 2. So, that means, T of this is this. So, that means, T inverse of this is basically A alpha 1 plus B alpha 2. This is coming from this fact. Okay. So, now this is nothing but A T alpha 1 is equal to T inverse of beta 1. So, this we can write as A T inverse of beta 1 plus B T inverse of beta 2, because alpha and alpha 2 is coming, alpha and alpha 2's image is beta 1 and beta 2, that is it. So, this is the definition of this implies T inverse is a linear mapping. So, if T is linear, then T inverse is also linear transformation. Okay. So, this is the inverse of a linear transformation is also linear, but for to exist the linear mapping we need to have this T should be a bijective mapping. Okay. So, now we will define isomorphism or isomorphic between two vector space. So, first let us define the when we call a linear transformation is isomorphism. So, isomorphism. Okay. So, it is basically a bijective mapping. Any bijective mapping is called isomorphism. So, suppose we have a vector space U and V, let this be a linear mapping between linear mapping from U to V from two vector space U to V, and these two vector space has to be over the same field, over the, that is most important, same field F, over the same scalar field F. Okay. Now, this T is called then T is called a isomorphism, an isomorphism if T is bijective. If T is bijective, that means it is 1 to 1 and 1 to. one-to-one and onto mapping. If both one-to-one and onto, then we call a mapping is a bijective mapping. So, if T is bijective, then we call T to be a isomorphism, and then this vector two vector space are isomorphic. If there exists a bijective linear transformation between U to V, then we call a vector space to be isomorphic, and then it is denoted by U. So, that means, if there is a linear transformation which is bijective, then we call the two vector space is isomorphic. So, U and V, this is isomorphic. You can use this symbol isomorphic. So, U and V is isomorphic if there exists a linear transformation, linear mapping T from U to V which is bijective. So, that means, if there is a isomorphism between U and V which is bijective, then we call these two vector space are isomorphic U and V. Okay. Now, we have some theorem. So, if U V are isomorphic, then they have a same dimensional vector space, and conversely, if they have a same dimensional vector space, then it has to be isomorphic. So, we will just write the theorem in a proper way. This theorem is telling, let U and V be two finite dimensional vector space, two finite dimensional vector space over the same field. This is important, otherwise we cannot define the mapping. Over the same field F, then U V are isomorphic if the dimension of U is equal to dimension of V. Then U and V are isomorphic if and only if their dimension is same, if and only if dimension of U is equal to dimension of V. Okay. So, this is the theorem. So, you have to prove this theorem. So, there are two parts. One part is if they are isomorphic, then their dimension must be same, first part, and second part is if the dimension is same, we have to prove they are isomorphic. So, let us try to prove the first part. Suppose they are isomorphic U and V. So, that means this implies there exists a bijective mapping from U to V, bijective linear transformation from U to V. Okay, since T is bijective, then the kernel of T is basically only the 0 vector of U. Kernel of T means the set of all vectors which are mapped to the 0 vector. Now, since T is bijective, that means T is 1 to 1, and we have seen in the previous class that for a 1 to 1 mapping the kernel is 0. The only 0 will map to this. Okay. Now, kernel is 0 means dimension of the kernel is basically kernel is 0 vector, dimension of kernel is 0, and it is on to. So, that means it is T is on to also. T is on to means the range of T is basically V, because it is on to mapping. Okay. So, this means dimension of range of T is same as dimension of V. Now, we know in the last class the rank nullity theorem, that is telling the dimension of the kernel of T plus dimension of the range of T is equal to dimension of the domain, dimension of V. So, now this is 0, this implies now this is 0. So, the dimension and this is the onto. So, dimension of V is equal to dimension of V. So, this is the first part of the theorem. So, if these two are if there is a bijective mapping, then their dimension is same. And the second part of the theorem is, if their dimension is same, then we have to show that they are isomorphic. That means, we need to define a linear transformation which is bijective. So, let us try that. This is the second part of the theorem. Conversely, suppose dimension of U is equal to dimension of V. We have two vector space U V which are finite dimensional and their dimension is same. Okay. So, now let us take a basis on U. So, say alpha 1, alpha 2, say their dimension is say n. There are n number of vectors in the basis for both U and V. So, say beta BU is equal to alpha 1, alpha 2, alpha n is the basis of U. So, this is U. Let BU be basis of U, and BV we take beta 1, beta 2, beta n be a basis of V. Okay. They are same dimensional. So, number of vectors in the basis will be same, and that is n. So, this is a basis, this is a basis. Now, we defined a linear transformation from U to V like this. So, T of alpha 1 is going to beta 1 like this, T of alpha 2 is going to beta 2, okay, and dot 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 dot. In general, T of alpha is going to beta I. So, dot 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 T of alpha n is going to beta n. Okay. So, this is the way we define the linear transformation. Now, this is a linear transformation from U to V. Now, how we get this transformation? Suppose we take a alpha from here, alpha is some a1. So, alpha is a member in U. So, it can be written as the linear combination of the vector in the basis alpha n. So, how we define T alpha? T alpha, it is a linear transformation. T alpha is defined as A2 T alpha 2 A n T alpha n. So, this is basically A1 beta 1 plus A2 beta 2 A n beta n. So, this is the way we define the T from U to V. We take any alpha from U, and this is the way we define this. Okay. Now, we will show this T is a bijective mapping. So, for that, first of all we need to show T to be a 1 to 1. So, for 1 to 1 we need to show kernel of T is 0. 0 means the 0 vector of U. So, what is the, so suppose alpha belongs to kernel of T. Let alpha belongs to kernel of T. So, that means T alpha is going to 0 vector of V. Now, T alpha is nothing but this. So, A1 beta 1 plus. So, suppose alpha is a member of this. Suppose alpha is written as this. Okay. So, that means this. So, that means A1 beta 1 plus A2 beta 2 dot 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 A n beta n, this is 0 vector of V. So, now these are linearly independent, beta is I are linearly independent Li. So, this implies all the AIs are 0. Okay. So, all the AIs are 0. So, since all the AIs are 0, that means alpha is basically summation of AI alpha is 0 vector of u. So, that means only, so that means kernel of T is only consist of 0 vector of u. Okay. So, that means this T is, this implies T is 1 to 1. Now, we need to show that T is onto also. For that, we will use the rank plus nullity theorem. So, we know that kernel dimension of T plus dimension of range of T is equal to dimension of u. This is the rank nullity theorem. Now, this we have seen this is 0 because dimension is 0 because this T consists, kernel of T consists of only 0 vector of u. So, 0 plus dimension of is equal to dimension of u, which is same as dimension of V. So, that is the assumption we made. So, this means dimension of range of T is basically dimension of V. So, this implies range of T is basically the whole set V. So, this implies T is onto mapping. So, this implies T is onto. So, we have seen T is onto and T is onto. So, T is bijective and this implies that U and V are isomorphic if they have same dimension. If they have same dimension, they are isomorphic. Okay. Now, we will quickly show another result on this isomorphism. Suppose this is another theorem. Let V be a finite dimensional, be a n dimensional vector space, over the field F, vector space over the field F. Then V is isomorphic with F n. F n is the basically Cartesian product F cross S, the Cartesian product of this. So, this is a this will so this, how to prove this? Okay, so since time is over, so we will prove it in the next class. Thank you.